examples. I will then take a look at the worksheet I gave you guys in there. But before, let's finish with this, the law of universal gravitation. So this one is actually very interesting because the law of universal gravitation is not, it is and it is not. It is Newton's fourth law, but in many textbooks they don't even mention it. They say as first law, second law, and third law. And that's because Newton's fourth law, came or was published not together with the other three laws, and he was, I don't want to say hiding it, but it wasn't such a big deal for him apparently, because he was looking for a theory of gravity, right? And he developed one, and then it implied, or in some way it was used to prove the law of universal gravitation, right? So he didn't make such a big deal as he should have about it. So this is a major contribution because it allows us to explain the orbits of the planets around the sun, for example. You should remember that the Greeks, and then even Tycho Brahe and other astronomers, right? Not Copernicus, but other astronomers, they didn't believe, they didn't accept that there were evidences that the Earth was actually rotating around the sun, right? The idea was that the sun was orbiting around the Earth, and the Earth was the center of everything. Then came the idea of epicycles. I don't know if you have heard about it, but that was the idea of the Earth rotating around an empty point in space. That doesn't make any sense now. We know that if there's an object rotating around another object, right, like for example the moon needs to rotate around the sun. The moon cannot just rotate around anything. There has to be a mass. And that's what Newton explained, that objects that are less massive than the sun are orbiting around the sun. Okay? That is the law of universal gravitation. You have two objects that are either attracting or repelling. If they are attracting, all right? So you have that objects seemingly seem to be falling towards another object, right? So the force that the Earth exerts on objects near its surface is just an example of universal gravitation, guys. The fact that we have satellites orbiting the Earth, it allows us to explain or to visualize gravity as it works, right? So the law of universal gravitation, in just simple words, is the idea that there is an instantaneous force acting on a body which is orbiting around another body that it's normally, is always more massive than the other body. So that's very, very important, because thanks to that, we're able to explain the orbit of the moon around the Earth. We're able to launch satellites and launch rockets to other planets, because we understand how gravity works. We probably don't know where it comes from, so that's different, right? But we know at least how gravity works. All right? So to understand this, we need to have an understanding of physics and mathematics. The orbit of the moon around the Earth is circular, almost circular. In fact, the planets around the sun, they actually have elliptical orbits that are very circular-ish. So we can use concepts on mechanics to explain that. So let me actually show you that on the board. Okay. Let's see. So now we know that objects like the sun, the Earth, and other planets, or the moon, they have the gravitational pull. right? So let's say we have the Earth. And we have an artificial satellite going around. How can we study the orbit of this satellite around the Earth? So, or how can we study the velocity, right, as it goes around? What makes the object go around? The gravitational pull of the Earth. So, from the center of the Earth towards the place where there is a satellite, we trace or we check the distance. The radius of the Earth is approximately 6,400 kilometers. And the mass of the Earth is approximately 6 times 10 to the 24 kilograms. So we can claim, and I'm actually exaggerating that orbit by the way, we can claim that a satellite here, as you go, right, is at an altitude of, let's say, 10 kilometers above the surface of the Earth. So this is the surface. So there's 10 kilometers from the Earth's surface to the satellite, right? So the whole distance will be 6,410 kilometers. All right. In a circular motion, the only force that acts on this body, and we're going to assume that is, and it's correct to assume that, is going at a velocity that is constant. Constant. We call that the orbital velocity. We have the orbital velocity of that. So now let me show you guys Newton's fourth law. So by studying the orbit of the planets, the orbits of even the moons, by checking their period, and by knowing Kepler's law. So by the way, the precursor of this, the person who came after, a precursor, was Johannes Kepler. You can Google it. He developed 3 laws as well. One of the laws was that the orbit of the planets around the sun is elliptical. And then he has the law of areas and the law of periods. Period squared over the distance cubed to the sun is constant. And don't worry about that. But the law of gravity, the gravitational law, states that the force of gravity, the gravitational pull, is proportional to the multiplication of masses divided by the distance squared from the center of masses. And you know what's the constant there? So it was discovered later that the constant, gravitational constant, is equal to 6.67 times 10 to the negative 11 newtons meter squared over kilogram squared. This is called the gravitational constant. So that's awesome, because now I know what's the force that anybody that is approaching the Earth is experimenting due to a gravitational pull. All right, which is that. And what's the force equals to? The the body is going in a circular motion. What force do I have in a circular motion? Does anybody remember? What's the name of the force in circular motion?
Centripetal force.
Perfect, yes. We have the FC, centripetal. And that's mass velocity squared over the radius, which is what? This. All this is R. So pretty much what you do is you make this force equal to that force. That's how you get orbital speeds. All right. Let's leave it there because you guys can see it. But that is the physics behind satellites. And that's how we can actually launch satellites. We cannot do escape velocity yet. You probably have heard about it. When you guys saw the mission just a few months ago, in the one from SpaceX, right? The one from SpaceX that happened in April, I believe. Yeah, April. They launched this rocket from Cabo Cañaveral to the ISS, and now just recently came back. When they launch it, they have to break through a barrier. They have to break through the gravitational pull of the Earth, which doesn't seem a lot, but it is. It can be a lot. All right? So we will study that more with energy. For now, this is very important. All right? Just to understand at least the ideas behind gravitational law. How do we use it? All right? Something that is also used for is the idea that gravity is also affected by this, right? So we know that when we talk about the force, the gravitational force depends on, we know already that Fg is a force, which is the force of gravity. And the force of gravity depends on what? The mass and gravity. Mass doesn't change, but gravity does. That's important. We know gravity is not constant, right? The value of gravity depends on where we are located on Earth. Inside the Earth, or on Earth, right? When we are on Earth, it doesn't really change by much, maybe 9.80, 9.81 meters per second squared, right? So by 100th, right? But as you go farther from the center of the Earth, that value of gravity starts decreasing. All right? So how? Let's put the equation here. I'm gonna write the equations for, or the equation for Newton's fourth law. So the gravitational law is written as G m1 m2 over r squared, where r is the distance. The masses are m1 m2, and you know g is just a constant. So let's suppose you are here on Earth. Two situations. One situation where this is the Earth, and you are standing here. And the other situation where you are here, but then look, you are farther from the center. Here you are closer. At this point, your weight could be 700 newtons. In this case, your weight could be 400 newtons. Where did the other 300 go? This will be M2, M2. So mass and gravity is the weight, the gravitational force. So let me introduce you guys to the equation of gravity. This is M1, this is M1. What you're seeing there right now is the equation of gravity. So it makes sense. The farther you go, the smaller gravity will be. Alright? That's why when you are farther, as you get out farther from the earth, gravity starts diminishing until you start floating, right? Let me show you this slide. There. That's Newton's law. You know what's interesting? That's called the law of universal gravitation. Nowadays we know that that's not very accurate. The law of universal gravitation works for objects that are not very massive and that are not behaving at very high speeds. When you go into higher astrophysics or particle physics, when you go into very high speeds or very high masses and speeds as well, by the way, like for example, electrons in the accretion disk of a black hole, or let's just say stars orbiting a black hole, like in the galactic center, this idea doesn't really work anymore, right? In fact, let's just go local. When you want to explain orbits of the planets, everyone works except the one on Mercury. It works and it doesn't work. It works at some points, it doesn't work to explain certain anomalies. One of the anomalies of Mercury is that Mercury is preceding the perihelion. Okay, so just a few concepts, right? When a planet orbits around the sun, there is the aphelion and perihelion. The perihelion is the shortest distance between the planet and the star. So the perihelion of Mercury is preceding. It's not always in the same position. You cannot explain that with the law of gravitation, even though it's a law. It doesn't work in that particular situation. So what do we need? We needed Einstein. 200 years after Newton, 200 each, right? He developed the general, the special, and then the general relativity, where he joined the concepts of light, the speed of light, and the effects of gravity. And then, even though I said that we know how gravity works, but we don't know where it comes from, at least now we are certain gravity warps space-time. So it's correct to say that gravity works as a force, but it's not totally correct. Gravity, for example, the Earth that you see there, imagine the space where we are is like a fluid. The Earth is pushing against that fluid, the gravitational pull. And even though we don't see it, we can measure the effects. And we have seen that by looking at light. Light gets deflected by gravity. So if gravity is affecting light by bending light, there has to be a higher concept of gravity that Newton didn't have access to because of the tools, because of the math, right? Because of time as well. I mean, he developed a lot of things, but that was not the case, right? So that's very interesting, right? Now, application for this will just be they give you two masses and they ask you to find the force between two masses, right? So they give you two people of 70 kilograms and then you can measure it, right? Depending on the distance, of course, but again, the mass is very low to make any difference, all right? We see the effects of this more when we're talking about the gravitational pull. And by the way, in the slides as well. So you can also see it there. That's the equation for gravity. And the mass of Earth, approximately 6 times 10 to the 24. What can I ask here? A conceptual question will be, what are the parameters that affect gravity? The mass and the distance from the center of the planet. The closest you are to the center, the higher gravity is. All right? So that's why we know that gravity inside a black hole is enormous. Because a black hole is millions, in some cases billions, the mass of the Earth. And the radius is very small, right? It can be a few thousand kilometers, no more than that. There can be black holes the size of the Earth, but with the mass of the whole sun, or even twice the sun contained in there, right? So that's what we know as a singularity, okay? That's very nice. Here in this table, they give you values of the acceleration of due to gravity on different places. So for example, we can see, as I said, gravity depends on the mass and the rate. For example, right? When you want to know the mass or the gravity on certain planets or the stars, you need to know the mass of the star or the planet and the radius of the planet or the star. And then by knowing those values, you use a formula gm over r squared, and then we can get, in fact, I'm going to do the calculation so you can see it for the Earth. All right? Then we have the sun, the moon, very small. Man, you know what the problem there? Look at the gravity of Mars. When people ask me if we are going to be able to colonize Mars one day, I wish Mars was more like Venus, even though we know Venus is hell on Earth, right? Venus, is a nightmare for people who fight, for people like that are against this whole climate change that is going on. We don't feel it right now, but the effects are going to be felt probably in the next 50 to 100 years. Not like Venus, but there are going to be some changes, of course. Venus has a very strong greenhouse effect due to the very dense and poisonous, by the way, atmosphere. So nothing can live on Venus. Well, maybe you read the news and you probably heard that we're trying to see if there are some signs of organic life, but that's not on the surface of Venus though. They're trying to look on the top of the clouds of Venus. So when you go within the clouds, there is a lot of ammonia, there's a lot of carbon dioxide, a lot of sulfuric acid rain that will kill anything organic. But on top of the clouds, we think that there are evidences for it. But anyway, that's another thing. What I mean is that the gravity of Mars is very weak. So I don't know if Mars will be an appropriate place to colonize. I always feel like it's more like a science fiction, like Total Recall and stuff like that, but it's not really very suitable. Jupiter and Saturn, forget it, because they are gas giants. There's no surface. So the other planets, the only places where we can think about colonizing one day is Mars and maybe the moons of Jupiter or Saturn. The problem is that they are very far from the sun, right? Venus and the Earth and Mars, they happen to be in the Goldilocks zone. The Goldilocks is a definition of not too hot, not too cold, right? So it's a nice distance, but still, I still find it very hard to think or believe that we can have bases on Mars, but living on Mars is a different story though. So let's do a calculation. And we're about to finish with chapter 2, by the way. It's not bad. So remember, quiz on chapter 2 on Tuesday, okay? And then we go into chapter 3. Don't forget to do the assignment. And actually, before we finish, I want to show you a few of those problems with that there are in the extra credit sheet. Okay. Knowing that we're going to use approximations anyway, but let's see what we get. The mass of the Earth is 6 times 10 to the 24. It's actually 5.978, but times 10 to the 24, but it's good anyway. And knowing that the radius of the Earth, but remember, this is in kilometers, so I have to do, right? I multiply by 1,000. Let's use the equation. Let's try to find gravity. Gravity is the gravitational constant, the mass of the Earth, divided by the radius of the Earth square. G M over radius square. Let's do this. 6.67 times 6 divided by 64 squared times 10 to the negative 11 times 10 to the 24. That gives you 10 to the 13. You add the exponents, right? But one is negative. And then you have 10 to the 13 divided by 10 to the 5 squared, 10 to the 10. So now I will do the calculator here. 6.77 times 6 divided by 64 squared. I get 0.00977. So I get this. 0.00977 times 10 to the 3. If I move the zeros, 1, 2, 3, I get, for my gravity, I get this. 9.77 meters per second squared, which I can approximate as 9.8 meters per second squared. There you are. This was very important. You can see that equations that were discovered more than 200 years ago, they give us values that we can actually work, right? So that's basically it, guys. I want to show you for chapter 2. What I want to do now, we have a few minutes, we have some time left. I want to show you just a few hints for the problems in the worksheet, all right? If you